Hello class, here we are again. I'm going to go over the proof of the theorem that uh, there is always a primitive root modulo a prime p. So I'm going to illustrate this for the prime p equals 7. All right, so I started out writing the power grid for p equals 7. So here I have all the distinct congruence classes modulo 7 written here in the first column, and then I'm going to write the powers of these congruence classes in the rows on the right. And so you know that once we get a 1, it's going to repeat, and so I'm going to stop once I get a 1. And so all the powers of 1 are 1, so it's no point in writing them all out. And then 2 squared is 4, and then 2 cubed is 8, which is congruent to 1 modulo 7. So I have a 1 here, so I don't need to write the other 3. But you notice that the order of 2 was 3, which is a divisor of 6, the order of the group. And now here, 3 squared is 2, is 9, which is congruent to 2, and 3 times 2 is 6, and 3 times 6 is 18, which is congruent to 4 modulo 7, and 3 times 4 is 12, which is congruent to 5, and then 3 times 5 is 15, which is congruent to 1. And then we can continue and fill out this table. So 4 squared is 16, which is congruent to 2, and 4 times 2 is congruent to 1. And then 5, I'll just write this down since you can actually pause the video and calculate this out on your own. But you notice here there were 2 congruence classes here where we had to go all the way out to where Fermat's little theorem holds, that is the p minus first power before we got 1. And so these are primitive roots modulo 7. Okay. And the theorem is that no matter what prime number p you have, you're always going to get some primitive roots. Okay. So let me write the theorem out. The congruence x to the n congruent to 1 mod p with p prime has at most phi of n solutions that are not solutions of a congruence x to the m congruent to 1 mod p of lower degree. Right? So we'll prove this. So here's the proof. All right. So suppose x to the n congruent to 1 mod p has a solution A that is not a solution of x to the m congruent to 1 mod p with m less than n. Right? So just for example here, suppose that we know that 3 to the 6th is congruent to 1 modulo 7, but 3 to the m is not congruent to 1 modulo 7 for any m smaller than 6. Right? Then a squared all the way up to a to the n are the solutions to x to the n congruent to 1 mod p. So since each of these satisfies x to the n, since a satisfies x to the n congruent to 1 mod p, then all the powers of n are going to satisfy this. And these are all distinct, and so we know by Lagrange's theorem that there are at most n solutions to this, so these are what the solutions are. Right. Now, okay, so suppose the GCD of I and n is not 1, right? Then the important thing to notice here before we go on is that n over the GCD of I and n and I over the GCD of I and n are both integers. Right? So that means that the congruence x to the n over GCD of I n congruent to 1, this is a congruence x to the m congruent to 1 where with m less than n, right? So, and if I take a to the I and raise it to this power, I get a to the n to the I over GCD of I n, and this is an integer, so this is going to be congruent to 1 mod p. Right? So, so if we want something that's not a solution to x to the m congruent to 1 for m less than n, then that power, that has to be that power of a has to be relatively prime to n. So therefore, there are at most phi of n solutions to x to the n congruent to 1 mod p that are not solutions to x to the m congruent to 1 mod p of lower degree. Okay, so you notice here we haven't even proved that there's one, but we've proved that there can't be more than phi of n of them. Okay, so now we need this lemma, which says for any natural number n, the sum over all the divisors of n of phi of n equals n. All right. Actually, I should point out that sometimes I write phi this way, and sometimes I write it in the other way with the vertical line through the circle. They mean the same thing. All right, so this is a formidable looking sum, but it's actually really an obvious fact. If you look at a couple of examples, you'll see. So you consider the fractions 1 over n, 2 over n, all the way up to n over n. Each has a reduced form n prime over n. So this is for some divisor of capital M. Right? So for each divisor n of n, there are phi of n reduced forms, n prime over n. Right. So let's just do an example here. N equals 6. So there we have the fractions 1 over 6, 2 over 6, 3 over 6, 4 over 6, 5 over 6, and 6 over 6. And we put them in reduced forms. And you see that the denominators are all the integers that divide 6, and the number of times that each appears is phi of that denominator. Okay. So therefore, there have to be phi of n solutions to a to the n congruent to, or x to the n congruent to 1 modulo p, because there can be at most phi of n for each n, but the sum of all the phis is n. So here the capital N that we're using is this phi of n, is the n before. So there are phi of p minus 1 primitive roots. Okay. So let me just show you the table for, or the power grid for p equals 11. It was here we had so p equals 11, p minus 1 equals 10, and phi of 10 equals 4, and there are 4 primitive roots. But actually, the theorem tells you that there are going to be, for each divisor of 10, there are going to be phi of that number primitive roots. So there are roots of order that number and no smaller order. So there are 4 classes of order 5, and there is one class of order 2 and one class of order 1. Okay, I'm going to have to pause now and stop this. Okay, so what do I do? This?